the REP-Z and the REP-NZ prefixes. I want to begin with the REP-NZ prefix because we've already seen it. The general syntax is as follows: REP-NZ and then the string instruction. You may use any of the string instructions that we have seen so far. REP-NZ actually means repeat as long as not 0. This is a good way to remember it. The NZ stands for not 0. Maybe another formulation, repeat as long as the 0 flag equals 0. A short summary of what this instruction does. It repeats the string instruction as long as the 0 flag is cleared, and also ECX is not 0. Some basic pseudocode of what happens in every iteration. First we check if ECX equals 0, we terminate, which means that we finish the instruction. As an example, if you begin this instruction, REP-NZ string instruction, when ECX is 0, then nothing is going to happen because of this clause. If ECX is 0, we terminate. Next, if ECX is not 0, we decrease ECX by 1. Then we execute the string instruction, which is this one here. And finally we check if the 0 flag equals 1, we terminate, which means that we exit this instruction. If you are more comfortable with the assembly syntax, let's try to explain it here. In every iteration, we first check if ECX equals 0, and if it does, we exit. Then we decrease ECX by 1. Then we execute the string instruction, which is this one. And finally we check the 0 flag. If the 0 flag is 0, we move on to the next iteration. But if the 0 flag is 1, we terminate. We move on to the REP-Z prefix. It is basically the same as the REP-NZ prefix. It just has a different termination condition over the 0 flag. REP-Z could be remembered as follows: repeat as long as 0, as opposed to REP-NZ, where the condition is repeat as long as not 0. REPEAT-Z says repeat as long as 0. Another formulation is as long as the 0 flag is 1. A basic summary of this instruction: it repeats the string instruction as long as the following happens. The 0 flag is set, which means that it is 1, and at the same time ECX does not equal 0. I don't want to go over what happens in every iteration. I just want to make sure that you see the difference, because it is really the same as the REP-NZ instruction. Take a look, for example, at this assembly code and see the change. As you can see, the only thing that changes is here, the condition over the 0 flag. Let's look at a simple summary of the termination condition, because this is basically what you want to remember. You don't have to remember this by heart. It is enough to understand it intuitively, and whenever you really need to know exactly what is the termination condition, you can always come back to this table. The first prefix is rep. It doesn't have any termination condition which is related to the flags, as we have seen. The only termination condition for rep is related to ECX. Rep terminates whenever ECX equals 0. And as you remember, rep decreases ECX in every iteration. Next we have rep Z. It has another name, rep E, which stands for repeat equal. Rep NZ also has another name, which is rep NE, repeat not equal. I want to emphasize, rep Z and rep E are exactly the same. They have the same encoding. The same is true for rep NZ and rep NE. They are exactly the same. Let's take a look at the termination conditions for rep Z. Rep Z is going to terminate if the 0 flag equals 0 or ECX equals 0, as opposed to rep NZ, which will terminate if the 0 flag is 1 or ECX equals 0. Rep Z and rep NZ might stop as a result of one of two termination conditions. This is not true for rep because there is only one termination condition for rep. But for the rep Z and rep NZ, it is a bit more complicated. There are two conditions. In some cases, we might want to further investigate after the repetition ends because we want to know what really happened. We want to know if the repetition ended because of the 0 flag or because of ECX equals 0. Checking the termination code. I want to go back to this example. I remind you that in this example we search for a null terminator inside a string. Here the string is called A star, and here max star is the maximum amount of bytes that we are willing to go through in our search. We use the rep NZ scasb combination to search for the byte AL inside a string pointed by EDI. We just keep comparing AL with every byte inside a string until we find a match. If we didn't find a match within the first max star bytes, then we give up. This instruction doesn't go on forever. It finishes at some point. And at that point, we want to know what caused the repetitions to stop. This kind of knowledge will give us the power to decide later in the program what we want to do. Basically, there are two cases of what could have happened. The first one is this, ECX equals 0. This means that we have reached max star. It means that we have searched for the null terminator inside max star different bytes, the first max star bytes. The other case is 0 flag equals 1, which means that a null terminator character was found. So how can we know? The simple answer is that we check. After we finish with this instruction, we have to do some checking. We can use the 0 flag to find out what really happened. In this case, we really care about the null terminator. We want to know if a null terminator was found or not. If we really cared about ECX, for example, we could just use the JECXZ instruction to check if ECX equals 0. But in this case, we really care about the 0 flag. So we can just use this instruction, J and Z, null not found, which is going to jump to null not found if the 0 flag equals 0. However, if the 0 flag is 1, which means that a match was found, we are going to slide to this location, which is marked by this comment, null found. Basically, this is just a big if-else construct. In this part of the construct, we have the null found case, and in this part we have the null not found case. Compare S. Compare S stands for compare string operands. This is a pretty useful instruction to compare between two different strings or two different arrays. It has some forms, as usual. The first one is called compare SB, where B stands for byte. In this form, we compare the byte pointed by ESI in memory with the byte pointed by EDI in memory. We then set the flags accordingly. Then we advance ESI and EDI 1 byte according to the direction flag. I remind you, if the direction flag is 0, ESI and EDI are increased by 1 byte. However, if the direction flag is 1, then ESI and EDI are decreased by 1 byte. I want to remind you what set flags accordingly means. It means that basically we imagine that we subtract. We subtract the byte at ESI minus the byte at EDI. And the result sets the flags accordingly. I also want to remind you that this kind of subtraction has effect on many flags. For example, the sign flag, the zero flag, the carry flag, and the overflow flag. Let's move on to the next form, compare SW, where W stands for word. This form compares the word in location ESI with the word in location EDI, and it sets the flags accordingly. It then advances ESI and EDI 2 bytes according to the direction flag. The last form does exactly the same, but for D words. It compares the D word at location ESI in memory with the D word at location EDI. It then sets the flags accordingly. Finally, it advances ESI and EDI 4 bytes according to the direction flag. Let's look at an example of using the compare S instruction. We want to check the equality of two different buffers which have the same known size. Here we can see a declaration for two buffers. The first one is called buff1 and the second one is called buff2. I want to add a comment regarding the name buffer. You might be wondering, what is a buffer? Basically, people use the name buffer when they refer to a chunk of memory. If this chunk of memory contains readable text or ASCII text, then you might refer it as a string. You will usually call a chunk of printable characters a string. However, you will generally call a chunk of memory a buffer. It doesn't really matter because basically everything is the same. Those are just bytes in memory. But this is just semantics. I call this buffer number 1 and this is buffer number 2. And they are made of D words. Both of them have exactly num-DW D words. Which means that, for example, the actual size of buff1 is exactly 4 times num-DW bytes. Next, let's look at the code. We first load the label buff1 into ESI and then the label buff2 into EDI. We also load the amount of D words that we want to compare, which is num-DW into ECX. We can actually use this number, the number of D words, because here we use the letter D. If instead compare SD, we used compare SB, then we would have to use here num-DW times 4. But because we work with D words, we may count with D words. Now let's discuss this instruction. I remind you that the instruction compare SD is just about comparing one D word every time. It compares one D word from buff1 against one D word from buff2. And then it moves to the next two D words. This instruction will finish only when a mismatch was found, which means that it will only finish if the D word from buff1 does not equal to the D word from buff2. And there is another termination condition. It will also end after exactly num_dw D words. So in the case where all the D words are equal, this instruction will go exactly num_dw D words, and then it will stop. How can we utilize the result of this instruction? As usual, we have to check some things after we finished with this instruction. We just check the zero flag. If the zero flag is set, it must mean that the buffers are equal. In that case, we just jump to this label, buffers equal. And in this clause, we have that the buffers are equal. However, if the zero flag was not set, which means that the zero flag was 0, it means that we had a mismatch. In that case, we just slide on to this place, which we call buffers defer. Another important thing to see here is that immediately when we get here, we subtract 4 both from EDI and ESI. That is because we really care about the location where the two buffers differ. We want to find the D word in which buff1 and buff2 do not agree. However, this instruction, repz compare SD, will give us the next location. Because, as you probably remember, compare SD automatically increases ESI and EDI. So if we want to get the relocation where the two buffers disagree, we have to subtract 4 from EDI and ESI. Basically, as I mentioned before, all this part is just some kind of an if-else construct. Let's summarize this lesson. We have seen the SCAS and compare S instructions. SCAS stands for scan string, and compare S stands for compare string operands. We have seen some prefixes, which were pretty much the highlight of this lesson. The prefixes are really powerful. They are like some kind of machine gun. They just keep going. We have seen the REP, REPZ, and REPNZ instructions. We also mentioned that REPZ and REPNZ have another name. And by the way, if you were wondering which prefix goes with which instruction, you may use any combination that you want from those 3 prefixes and those 5 instructions. Any prefix will go with any instruction. I also want to note that some combinations are not really meaningful. It is an interesting exercise to find out those which are not very meaningful. They are very interesting, at least in my opinion. Lastly, I have some meaningful idioms for you to remember. These idioms will really help you understand things intuitively, instead of remembering very strict rules of flags and ECX and so on. Basically, those are the idioms. The first one is repstos, which corresponds to initializing an array, or maybe literally, repeat and store bytes into array. The next one is rep move s, which has the meaning of copying data. Maybe literally repeat moving bytes from one location to another location. The next one, repnz scas, has the meaning of searching a character inside a string. It has the literal meaning of keep searching for a byte until you find it. Lastly, repz compare s, which has the meaning of comparing buffers. and maybe literally repeat comparing every two corresponding bytes between the two buffers. That's it for this lecture. See you next time.